You're standing at a traffic intersection and you start to accelerate when the light turns green. Suppose that your acceleration as a function of time is a constant for some time interval, t less than t1, and after that it's 0 for time after t1 less than some time t2. At the exact same instant the light turns green, a bicyclist is coming through the intersection, and the bicyclist has some initial speed and is braking with an acceleration of minus b2 for the entire time interval t2. And at time t2, the bicyclist comes to rest exactly where you are located. And we also know some initial conditions. So our initial conditions in this problem are that you're accelerating b1 at a rate 2 meters per second squared. And you do this for time t1 equals 1 second. And the bicyclist comes into the intersection, we'll call that b2 naught, that's the initial speed of the bicyclist, at 3 meters per second. And the question is, what is the rate of deceleration of the bicyclist, b2? Now, this can be quite a complicated problem, so the first thing we want to do is just make a sketch and think about what's involved. This problem involves two objects, you and the bicyclist. The person, that's you, has two stages of motion. And the bicyclist only has one stage of motion. So to get started, it always helps to choose a coordinate system and to make some sketches of the problem. So let's say we choose it's all one-dimensional motion, two objects, one-dimensional motion. And so we'll pick an origin at the light, at the one side of the intersection. And we have two objects, which we'll talk about u, x1, and the bicyclist, x2. Actually, we don't know yet who's in front of the other. The bicyclist will be first in front of you. So now, how do we sketch the motion of these two stages of motion? So let's make a sketch. And let's start with the person. Well, the person, if we plotted their position as a function of time, this will be position in general, I'll just draw the person function, they're accelerating to a time t1, and then they're moving at a constant speed at time t2. Now, the bicyclist is a little more complicated because initially the bicyclist has this is at time t, person 1. Initially, the bicyclist has a non-zero slope, and they're decelerating, and they reach u with a 0 slope. So this graph, this is the x2. That is the bicyclist. And right here, we have the person, x1. So now, to build a strategy, we can even look at our graph and see that from our initial conditions, we have some special conditions so from our strategy will be to, one, figure out what this time is. And we know that the bicyclist at time t2 has come to a stop. So that's one condition. And we also know that the bicyclist comes to a stop exactly at the same position as the person. x1 of t2 equals x2 of t2. So those are two conditions that we can deduce from all of this given information. And now we can apply our kinematic relationships for both the bicyclist and the person and try to see if these conditions will enable us to deduce what b2 is. So let's begin with the bicyclist. So the velocity of the bicyclist as a function of time is simply the integration of that bicyclist, dt prime, from 0 to t2. This is one stage of motion. The acceleration is minus b2, so this is a very straightforward integral. This is just b of 2 t2. v2, this is minus the initial speed equals that. v of t2 minus v of the initial speed is that. And because we want this to be 0, we have the condition that t2 equals v2 naught divided by b2. So that's our first condition for the bicyclist. Now, we have to separately solve for the bicyclist's position. That's easy. x2 of t is the integral of v2 t prime dt prime from 0 to t2, and that's just minus 1/2. This is, we'll want to make sure that we get the displacement, but at x2 naught is 0, so we have x2 at t2 equals the integral of the velocity function, which is v2 naught minus b2 of t prime dt prime from 0 to t2. And so we get v2 naught t2 minus 1/2 b2 t2 squared. And when we input this condition in for t2, this becomes very simply, it becomes v2 naught squared over 2b2. Substituting t2 into each of these expressions gives us that relationship. So that's the position of the cyclist at time t2. Now, this is a little bit trickier to get the position of the person. So in order to do that, we first find the velocity of the person, function. It's a two-stage motion. So for the first stage of motion, the velocity of person 1 minus their initial velocity, which is 0, minus 1, 0, that's 0, equals the integral of b1 dt prime from 0 to t1, which is just b1 t, 1. And this velocity remains constant throughout the next interval. So we can write the velocity function in the following way. v1t equals b1t for 0 less than t less than t1, and afterwards a constant velocity. Now, this is the function that we need to integrate to get the displacement. So let's get ourselves a little room here and integrate that. And we have x of t is two integrals. First, from 0 to t1, the velocity function during that time interval. And then for the second time interval, d to t2, the velocity function is constant this is b1, b1, t1, dt prime. Notice this is not a variable, but it is the time at the end of the interval. And when we make these two intervals, we get 1/2 b1 t1 squared. Let's make this the velocity at time t. Then that's time t. This first integral goes from 0 to t1. And the second interval, we're going to make this the position at time t2. And we get plus b1 times t1 times t2 minus t1. We have a common term, t1 squared, b1/2 b1 t1 squared, b1 minus b1 t1 squared. So this reduces to 1/2 b1 t1 squared plus b1 t1 t2. And that's how we find the position of the person for our interval. Let's just review that to make sure, because we had to get the velocity function first, and then we integrated the velocity in each time interval correctly in order to get the position function. Now we can apply our conditions. Notice we already know t2 here, and we can now apply the second condition, which says that the position of the bicyclist at time t2, which we found to be v naught squared over 2b2, is equal to the position of the cyclist, of the person at that same time, so that's minus 1/2 b1 t1 squared plus b1 t1. Now let's make that substitution for time t2. So that's v2 naught over b2. And now our problem is to solve for this time b2. And we're given b1, we're given t1, we're given v2 naught, and the only variable here is b2. It's a little bit of algebra to rearrange terms. What I'll do is I'll bring this term over to here. So now we'll just do a little bit of algebra. We have a b2 I pull out. I have a minus b1 t1 b2 naught. And that's equal to minus 1/2 b1 t1 squared. And now I can solve for b2. And so I get b2 is equal to vt naught squared minus b1 t1 b2 naught over minus 1/2 b1 t1 squared. Now, let's just do a quick dimensional check. B times t has the dimensions of velocity. So this is velocity squared. That's OK upstairs. B times t squared is dimensions of position. So what we have is meters squared per second squared divided by meters. That gives us meters per second squared. So we're pretty confident that we at least didn't make an algebraic mistake. And now our last step is to substitute in the numbers. And what we get is, if we put in the 3 meters a second squared minus b1 times t1 times 3. So we get upstairs is minus 3/2, and downstairs is 2 times 1 second. 2's cancel. So we get for b2 3/2 meters per second squared when we put in the numbers. If we want to check our result, we can then see what time we get. T2 is 9, T2 is 3 meters per second divided by our B2, which is 3/2 meters per second squared. So that's 2 seconds. And now the last check would be to see that the position functions correspond to that. Let's see if we can just do that quickly in our heads. Our position function for the person is v naught squared over 2b2. So that's 9 meters per second, 9 meters squared second squared over 2 times 3/2 meters second squared. And that comes out to x2 of t. This is a check, is 3 meters. And the x1 of t, we left out the 1 there. We should have had it. It's a little more complicated to put in here, but we'll just run the numbers quickly through. 2 times 1 second minus, that's a minus 1. 2 times 1 times 2, that's 2 times 2. So this is also 3 meters. And we actually have the right answer here.